Okay, gang, welcome back. Today we're going to be talking about data types. And VHDL has quite a few data types to choose from, but luckily not quite as many as other languages, so it'll be more easily manageable, I think. The main data types that we'll be using throughout the course is going to be standard logic vector, which we've already seen in the integer type. But we need to talk about some of the various aspects of those types so we can better understand why they're there and what they do. So first off, we're going to start talking about standard logic. Now, standard logic may seem strange because we already had a type called bit, and bit represented a 1 or a 0. So why on earth would we change a data type from bit, which seems to make sense for digital, to something new like standard logic, which is a lot more verbose and harder to type, right? So the idea though is bit just wasn't doing the job. So initially when VHDL came out, bit was the data type. But as time went on and people started simulating more designs, they began to realize that it just didn't cover all the needs of a simulation. And so standard logic was born. Now standard logic expands the definition by adding some more characteristics to the data type. And these characteristics greatly enhance simulation and the ability for you to debug your circuit using simulation. It provides also something called signal resolution capability. That means that if you happen to have two lines driving the same wire, in other words, you have two outputs connected together, the language needs a way to resolve that in simulation. It needs to understand, okay, if I have, a 1 coming out of one output and a 0 coming out of the other one, what happens when that in the simulation? How does that manifest itself? What do I see? And so this language provides some extra features that allow us to represent that in simulation. So in order to use standard logic, as we've seen in all the examples thus far, we have to include these two lines at the top of our code. You have to reference the library for IEEE and then include the standard logic 1164 library as part of your code development. What that does is it pulls in all the definitions for standard logic so that you can use them in your design. Now let's take a look at all the different types of values that a standard logic signal can have. Now we obviously have the 0 and the 1, which we're familiar with. That's standard high and low, 1 and 0 binary type signals. But we've added quite a few more. There's a total of 9 possible values that a standard logic signal can have. And some of the extra ones provide extra information about our circuit. The first one up here, U, represents an uninitialized signal. That means that the signal hasn't been assigned a value yet by your code, and so when you look at it in a simulation, it will appear as a U in the waveform diagram. So that's going to give you a clue right there that you may have a problem with initialization. X is used to represent that case I was just talking about. If you have one output connected to another output of a block, an internal block. Now remember, you can't connect outputs on entities. Those are modes, that's different. But if you have a block in your design or a signal in your design and you connect them together and they're both being driven by different signals, then you have to resolve that conflict. So what happens is it resolves that as a forcing unknown. In other words, it doesn't know what the answer is going to be. If you put a 0 or a 1, a 0 on one side and a 1 on the other side, it's going to be, what the heck, I don't know what that's going to be. So X is forcing unknown. We also have the Z, which is a high impedance state. Now, if you remember back to the digital days, there are chips that there's the standard output of high, standard output of low, but there's also the ability to do what's called a high impedance output. Now the high impedance output is really designed for you to be able to attach multiple signals to the same wire. This is very handy in things like data buses. Like if you have multiple memory chips and you want to access them independently, you tie their data bus to the same, their data outputs to the same bus and activate only one at a time in order to get data transferred from that particular RAM. It's a very efficient way of accessing lots and lots of different things. And in order to represent that in VHDL, we use Z to represent the high impedance state that these outputs will have when they're not driving the bus, right? So if you're not going to drive the bus, you would want to make it a high impedance or turn off the connection to the bus. And that's what this allows you to do. So Z represents the high impedance state. Weak unknown basically means the signal is so weak that it's impossible to distinguish whether it's a high or a low. Now, when would a signal get weak? Signal can get weak if you're trying to drive too much. So for instance, if your signal is driving 20 inputs, it may start weakening that signal a little bit, in which case you'll see an L or an H, which will indicate that the signal is starting to fan out too much. And then if it reaches a critical point, then it will become a super weak signal where you can't really distinguish it from a zero. So these are all clues in your simulation that you might be doing something wrong and you might need to fix those things. We also have the data type of, the value of a dash, which means don't care. Now, don't care is good for doing some circuit optimization. You know, if we've in your earlier digital days, you discussed things like how do I optimize a logic circuit, right? So you could use Carnot mapping, and if you had don't cares in your Carnot map, then you could optimize around that because those signals didn't matter to you. So that's how the don't care works in VHDL. It allows the synthesis tool to optimize around a circuit where you know that the signal value at this particular point doesn't matter. So this is standard logic. So if we look at standard logic, we have to look at the resolution table we were talking about before. And remember, what we talked about is standard logic provided a resolution for conflicts with signals when two signals are driving the same line. And so this is the table that they use to resolve those signals. And as we mentioned before, let's say you have a 0 coming in on one and a 1 coming in on the other. Well, you'll notice right there in the middle, there's your X. That's your forcing unknown. It basically tells you that you're driving the signal with two different values and it can't possibly know what that is, and it's being forced. So lots of things like that. You can go back and look at Z. Sorry, I used the wrong pin there. So Z. And then what would happen if Z is with 1? Well, it's going to be a 1 because Z means high impedance. It doesn't matter. So it's going to do whatever's on that particular line. So you can go through and look at all of these cases and use this table to decide, hey, what value is going to be presented to me in my simulation in certain conditions. And so that's pretty important there. Okay, so so that's our resolution table. Let's start talking about some actual other data types and kind of list the data types that we have. We categorize data types into two areas. One's scalar and one's composite. And so scalar types represent things like bit, okay? Although bit isn't used anymore, it's certainly important to mention for legacy reasons, and its values are 0 and 1. We already saw that standard logic has 9 values, and we just went over what those values mean. Now, notice these representations of values. These are characters, okay? So these values represent characters and not numbers, okay? So it's think of a character on your keyboard. The single quotes around it indicate that it's an ASCII character. And all we're doing is saying that these data types can be represented by these characters. So don't assume these have value, because they don't. They basically they're symbolic and they represent states, okay? Boolean behaves just like you would expect Boolean to behave with the true-false capabilities. And then, of course, character uses all the ASCII characters there. It can represent all the ASCII characters. If we go to the next type, that's our numeric. So this is the enumerated types, the bit and the standard logic and the characters. But we also have numeric types, and these are integer and real. Now, integer is basically any number, any integer number that's positive or negative, including 0, 0, 1, minus 12, etc., etc. So you have a wide range of integer values that you can use in VHDL, and that can be very helpful in certain designs. The real representation here is provided for real numbers, and you have to be very careful about using that because you want to make sure you understand how it's representing the real number in binary if you're trying to synthesize this. Now, if you're simulating, real can be used in a lot more freely to make decisions and figure things out. But it's actually works in both contexts, but you just have to be really careful when you're using it in synthesizable designs. So make sure you understand the limitations there. The composite types, basically all a composite type represents is taking these individual enumerated types and then sticking them together. So for instance, you've got the bit vector here, and the bit vector basically uses double quotes to represent individual characters that are part of the bit. This looks like any binary number you would represent in your digital courses. When we get to standard logic, it's the same exact thing. We still use double quotes to represent the vector contents, and then the values in there represent the individual allowed characters for that variable type. The vector here looks a real strange, right? Because it has Z and all the other characters, but it's perfectly valid as a vector in VHDL. Now this brings to a point something really important, and that is this does not represent a number. So it's very easy to be confused and to think that something like, say, let's pick out this one here. You could look at that and say, hey, doesn't that look a lot like the number 13, right? So that may look like 13. If you think about that as a value, it may look like a number. It's not. It's a vector that has 4 signals as part of it. It does not represent a value of any kind. Now, we interpret it because of the way we represent numbers in our head, and when we look at binary, we interpret it that way. That is not how it works in VHDL. This is a 4-bit vector, and that vector represents, in this case, a bit type, just like this is a 8-bit vector, and each element in the vector represents a standard logic type. So try to tell me what the number that represents, right? Can't do it because it doesn't represent a number. It represents a group of signals. And that's really, really important that you recognize that. Now, if you need a number and you're trying to do things numeric, then you want to rely on a type like integer. And we'll show examples later of how that's done and how to use that. But don't get confused in thinking that a vector is actually some number and you can use it to compare to some other number. So you couldn't, for instance, take this value and compare it to 12. Is it greater than 12? That wouldn't make any sense in VHDL. The other type, array type, is the string, and that's a collection of characters just like you're used to. The double quotes represent the literals for the strings, just as they do for the vectors. And here are some examples of how that's done. Now, composite types primarily we'll be using are the array types, which we just talked about. But there are other types associated with composite types, and one of them is the record type. Now, record type allows you to group signals of different type, okay? Whereas a vector is grouping signals of the same type, so standard logic vector takes all standard logic signals together. A record type can allow you to mix things together into a grouping, all right? So you'll see this construct in other languages, like a structure in C, where you can pull things together. This is useful for simulation, but generally not synthesizable. So some of these later types here are really primarily for synthesis and not for simulation. Or sorry, for simulation and not for synthesis. But the file type can also be another valuable tool for you. So file types actually do just that. They provide access to file structures, which can be really handy. So for instance, if you're trying to create a design that's going to filter an image and you're going to be scanning in all the image bits and stuff like that, having that in a file for simulation can be very helpful while you're testing. So you could dump an image into a file and then use that file as an input for your design to see how it reacts in software before you try to put this in hardware. So file types can be handy for testing your designs in a test bench. The last one here is an access or incomplete type, and it behaves a lot like pointers would in another language. You can create structures like linked lists and other things like that with that particular type. Predominantly throughout this course, we're going to be using only a certain number of types 99% of the time. We'll see some of these other types as well, but for the most part, we're going to be relying heavily on standard logic, integer, and standard logic vector. So all three of those are going to be our go-to types for most of the design, for 99% of the designs that we're going to be doing. We'll still dabble in some of the others, but that's the workhorses of VHDL. It wouldn't be a complete discussion of types if we didn't talk about how to represent constant values. And constants are incredibly important in VHDL, as they are in any other language. Constants allow us to predefine values that can be used in our code, and it often provides better documentation for our code as well. Constants are created by first off starting with the keyword constant, and then we're going to be doing a name for the constant. Remember, we talked about naming conventions earlier. Constants should be all caps with an underscore. That's a pretty universal standard across languages for representing constants. And then you provide the data type. In this case, this is a standard logic vector. The assignment operator here, now this is a variable assignment operator. It's different than our signal assignment operator. It's not a less than sign, instead it's a colon equals, and so you need to pay very close attention to that. That's a very different symbol than a signal assignment. If you try to put a signal assignment here, it's probably going to get pretty confused. And then you put the value you're making the assignment to. So we're basically equating the name or the symbol 17seg with the value here. Now you could use this as a way to, for instance, represent how a 7-segment display would represent the number 1. We could write the hard-coded value in our code, but then when somebody looks at the code, they're not going to really know what that is unless you put comments out to the side. And so by using a name like 17seg, it more clearly indicates what that value is to the user or to the programmer reading the code that you're using. The second advantage of using constants is if you use this in multiple places in your design and suddenly you realize you've made a mistake. Oh my gosh, I've declared the constant wrong. I should put a 1 here instead of a 0. Otherwise it doesn't look right. Now you have to go through, if you didn't use constants, and find all the values that are this and make sure they're the values representing the 7 segments and hope that you don't miss any. Or if you had used the constants in your design, you would just change the constant value up here at the top of the file and you're done. Constants, hard coding any number inside of any design, whether it's a programming language like C or whether it's a language like a synthesis language like VHDL, doesn't matter. The concept's the same. Never hard code a fixed value. Always use constant declarations. It costs you nothing in efficiency. There's absolutely no cost at all as far as the efficiency and of your design. So constants, use them all the time. If you have a question and you have to say, hey, should I use a constant here? Always err on the side of using the constant, okay? Another constant that you'll see a lot in the examples that we're going to be doing, oops, there it goes with the wrong pen again. If you're going to look at the stuff we're doing, I'll use active a lot because instead of testing for a single value of a signal, like if my switch is pressed or my switch is not pressed, I will use a constant to represent that. So if it's an active high input, then I'll say, if this is active, as opposed to if this equals 1. And that really helps the readability of your code. And it also helps if you decide to change the active state later on. and you can change it throughout the whole design. Not to leave out the integer, you can also create integer constants. You can create constants of any type, but here's some examples that you might create. So in your designs, you'll be creating things like standard logic vector, and integer constants all the time, and we'll see example code that does that as well. So it wouldn't be a complete discussion of data types if we didn't address some of the basic operations in VHDL. And so there are 4 basic operations. There's the arithmetic operations, the logical operations, relational operations, and the shift operations. Now, most of these are going to be familiar to you from other languages, so it's not going to be that big a deal. But let's take a look at them anyway. Addition and subtraction are going to be your go-to arithmetic operators in most designs. And so those will be very popular. And another one called concatenation is also going to be something you'll use a lot. We're going to see an example of that in a few minutes. But concatenation is a powerful tool for putting vectors together and piecing things together in your design. And so, like I said, we'll see an example of that in a minute. The rest of these are very, very, very useful in things like simulation, but you have to be really careful about using them in synthesis. Because if you try to use a multiply and synthesize that, it's going to create some interesting hardware. Multiplication is a complex thing to do in digital design, and it's so complex that a lot of vendors for FPGAs will actually provide high-speed multiply blocks for you to take advantage of and include those in your design. So they're pre-integrated into the FPGA so that you can access those, and they provide a faster, more efficient way to do multiply. So most of the time in your designs, it's going to be really addition and subtraction and concatenation as far as arithmetic operations. Logical operations, you're going to be using those all over the place, or we've already used them in examples that we've seen at the beginning of our course. Not, NAND, all of their standard logic is available in logic operators for VHDL. Relational operators, same story. We'll be using these all the time to make comparisons between signals and make decisions in our code about what to do next. And we'll see some good examples of where this can come into play. One thing I do want to do is draw your attention to the not equal operator, because that's a very unusual operator. Most of the time we're used to an exclamation point equals, right? But not in VHDL. VHDL, it's slash equals, so keep that in mind. The rest of these are fairly common in other languages as well. Greater than or equal to, and the like. So it should be fairly easy to manage those. And finally, we have shift operators that are available. And you can shift values back and forth in an array based on a certain number. Now, typically, I don't rely heavily on shift operators in VHDL. I rely on the concatenation operator to manipulate vectors. And we'll see some examples of that when we talk about shift registers and stuff like that. So there are better ways to do it than do the shift operator. But the shift operator is available if it's best for you in whatever thing you're doing. Maybe a simulation run would be very helpful for that. All right, so there's 3 things that we're going to do before we end our discussion today. And the first thing is we're going to start exploring that concatenation operator we were talking about. Now, like I said before, the concatenation operator is an incredibly powerful tool for you to use in VHDL. And it allows you to piece together different vectors and create a larger vector as a result. So here's some examples that really demonstrate how that works. We'll start with a signal called mynibble. Notice this is a vector of 4 bits, numbered 3 down to 0. We have my byte 1, which is an 8-bit vector, of course. My byte 2, which is another 8-bit vector. Now this would be declared somewhere in your architecture's declaration area, and then later on in the design you might want to reference them and do things with them. So here's some examples of how that might work. So the first one is the mynibble is being assigned this value. Now the way to look at this is it's always left to right, so it very much matters what order you put these in. And so to write the actual result of my nibble out, you would start on the left. We would have 0, 1, and then the ampersand basically says I'm going to add a 1 symbol here. Now this is not a vector, but this is actually a standard logic value because it's got the single quotes, and that's fine. You can piece together singles or vectors all together. This would be another 1, and then I'm doing another 0, so our result for my nibble is going to be 0, 1, 1, 0, using that as our example. See how that worked? So I'm taking multiple signals, sticking them together to create another vector, and this is a very common thing to do in VHDL, especially when you have bus signals coming in and you're trying to split things off. Let's take a look at this using a signal as an argument inside the concatenation operation. So in this second case, where we're assigning a value to my byte 1, we start off with 0, 1, 1, then we concatenate my nibble, and then we add another 1 to the end of that. So what does that represent? Well, we can write that out just like we did before, and we can say, well, it's 0, 1, 1. My nibble, which we saw up here now, is 0, 1, 1, 0, and then we put the 1 at the end, and now my resultant vector is 0, 1, 1, 0, 1, 1, 0, 1. So this is 8 bits, and it is what is getting assigned to that. This gets assigned to nibble. So we're kind of seeing how the concatenation operator is used to piece things together. You can also look at this, and instead of looking at it as the hardcore mechanics here, you can also think in terms of signals in your design. If you have a data bus coming in and you want to split the data bus off so that maybe the upper 8 bits go somewhere and the lower 8 bits go somewhere else, and then you can reconfigure them to come back together again, the concatenation operator is very handy for doing that. So in byte 2, we're just going to show something else, another a little more complex way to do this. You can access subvectors within a vector, and we talked about that before. But in this particular case, we can get bits 2 down to 1 for my nibble, and then we can go to my byte 1 and get bits 7 down to 4. So how are we going to do this? Let's change pin colors so that we can actually see this in more clarity. Basically, we're going to start off with 1, 1 because right here we're starting off with 1, 1 in our byte 2. Then we're going to look at nibble bits 2 to 1. Well, this is nibble right here. So bits 0, 1, 2, 3. That's the bit numbers. So bits 2 and 1 are going to be 0, 1, 1. So that's another 1, 1. And then finally, we have 7 down to 4. And remember, the bit numbers here are 0, 1, 2, 3, 4, 5, 6, and 7. So 7 down to 4 are these 4 bits, which means that we're going to be writing over here 0, 1, 1, 0. And so now this is the value that gets placed in byte 2. Okay, so that's kind of how this works. I threw together some more complex examples so you could see how you can just tear apart vectors and then piece them back together in different ways, which gives you just almost infinite capability of routing your wires in any direction and making them part of any other variable that you want, or any other vector that you want. So that's the power of the concatenation operator. The other thing that we want to talk about is the idea of a signal attribute. Now, signals we've talked about already, but signals actually can have attributes. They're not just a value that they hold, right? So it's not just a 1 or a 0. A signal can actually be or have attributes about how it performed and how it was created. So there's lots of attributes that go with signals. I'm just picking out 2 of the most common ones and the most important ones. And this one is the event attribute, which basically tells us true if the target signal changed values, during the current delta cycle. So we're going to talk about delta cycles later when we get into the more technical complexity of how synthesis tools work and how the software works and analyzes your code. But an event basically means that something's happened on that signal. That signal changed. That's basically how you look at the event. If a signal name, quote, event happens, then it triggers that to be true, right? So if a signal has changed, then the event attribute says true, which means it has. It tells the system it has changed. The last value is just that. It's the last value prior to the change of the variable. So if the new variable value is a 1 and the last value might be a 0, or it may not. It might be undefined, or it might be forcing unknown, or whatever other standard logic values that are allowed. But the last value will tell you what that was. So where this really comes into play heavily is when you're checking for clock edges. Now we know that in digital, we have devices like flip-flops that use clock edges to latch in values, right? So how do we write a edge trigger device in a language like VHDL? And we do that with events. Signal attributes, one of them being event as the attribute. So if we look at this example down here at the bottom, you'll notice that we're checking here if the clock is a 1, if it was a clock event, and if the last value was 0. So this is how you check for a rising edge in VHDL. If the current value is 1, if the signal just changed, in other words, there was an event on the signal, and the previous value was a 0, well, that's a rising edge, right? And so that's how we check for a rising edge in VHDL. The synthesis tool knows that, and it knows to associate that with an edge-triggered input on a flip-flop. And so that's an important part of specifying sequential designs with clocks and clock edge detection. We have a better tool for doing edge detection in the library, the standard logic library. We have a function called rising edge, which we'll use extensively. But this is what the function rising edge contains. It really is a very simple function that contains very little code in it, and basically this is the crux of it, okay? The last thing I want to talk about is when we're specifying things like integers. Now, integers are an important part of your VHDL design process. I'll show plenty of examples of how we can use them and make them work for us. But one of the things that I want to instill in you early on is that whenever you declare an integer, you want to constrain the range of that integer, and that's going to provide you with a more efficient design and less likely to have some issues down the road. So what happens is when you declare an integer, if you don't specify the range, it's up to the synthesis tool to decide how big you need that to be. Now remember, the synthesis tool may not know what values you're going to be putting in on the integer, because that might be, say, an input to a component that you're using in your design. So it can't know prior to implementation what the value is going to be. So it will pick a default size, typically 32 bits, to represent that integer value. But if your counter is only going between 0 and 4, you've just wasted a lot of bits. So you want to be very careful when you specify your integer to put a range on it so that you tell the synthesis tool, no, this is a number that's only going to go between these values, so you can use the resources necessary to make that happen. In this example up here, the big count size depends on the synthesis tool, but the small count is going to be 8 bits. Because we've specified a range between 0 and 255, 8-bit value can represent that quite well. So the synthesis tool will use an 8-bit value to represent your small count value. All right, so that's the trip into data types. There's a lot to know, but we've basically hit most of the high points. And you should be armed and ready to go into some more advanced design. So until next time, we'll see you later. Thank you.